Lemonade.
Just 5 weeks of lemonade.
I don't have a no.
Pink.
Oh, I got access to the special colors.
Until it explodes. Until I say emerald. No, that glasses. Whenever I need to wear safety glasses in process, just one.
What?
Although it looks blurry. I need safety glasses, right? In science experiments.
They're literally the
The
same.
normal glasses fall off.
Excluding, if we just exclude the like,
Hello.
like the taste enough, sweet enough. But yeah, there's no way. It's
Okay,
not
finally
Yeah.
I landed.
Today I'll present
I'll show you
improved proof of f of x at least x. Or improved.
okay.
Because
This. I'll write it. Teacher will be like, what?
I guess it's improved in rigor, but not necessarily. It's not necessarily easier, but I think it's probably more rigorous.
It was like that was this thing when you most. It's like you know how he has like short hair, right? Like he like rubs it, and he like does this. You know what I'm talking about, right?
Oh,
Yeah.
what the?
And like he like comes it, like, like ah. Yeah. He's the type to kind of get angry at himself every console.
Okay, so RTP.
Leon ruins his vision with one simple trick.
I had to kill your vision and ruin it.
Okay,
Yes.
so remember from before. So see, first you would say suppose.
I'm gonna just say this.
Godzilla had a stroke while reading this fucking
Suppose that it just hey,
Games already started.
that is smaller than smaller.
It's like this mix. Well, you played last time. How'd it go?
We won quite by a lot.
Wow. But what mix?
Open.
What's the just average age?
Our team is like
30.
I'm the youngest.
Oh.
Anthony, very
Because I joined the drop like 28.
So this is the start of the proof is similar to before.
Why is he?
I just make it a bit easier by not abusing. I just make a different variable for each thing, so it's less abused.
Wow.
So that means,
Yes.
so we say, so I use a different.
It's getting stolen.
I make this an alpha because it's an unused, a very brand new variable. So this is going to be a plus alpha. Wait. So this is. Yes, this is similar to before. This is equal to alpha x. This is greater than alpha x. So we ignore this. Alpha x minus fmk.
Yes, this is where you're like, we have
So this is a starting value. That means
yeah, you're like,
so that means we're saying there exists a c. If this is 0 less than c less than 1. So this is alpha. Yeah, alpha is. So alpha is between 0 and 1.
So there is this
Delta.
It's just a d. Not a delta.
Oh, it's just
oh,
it looks like a
That's the start. And now
yeah, that's true.
we are saying this. So now suppose we have such a c. Okay, for some reason I use a g. Wait, I use a g instead of a c. I'm not sure why. Let's make it a g.
So how do we reach contribution last time? Did we have something similar?
Yeah, this is the start is similar, but this is now f of x.
there's no recoil.
So this means let's say we fix. No, not fix. Wait. Okay, f of x plus y minus f of x. So this is similar to what we did before this. What I did in the proof a few hours ago. What's this?
What's f of x plus k? Is that... Oh yeah, just f of x plus k. No, we're ignoring that.
Oh, this is so.
Oh, you're saying that's positive, so yeah, it doesn't matter. We're bounding it without it. Oh, it's negative alpha x. Negative alpha x.
So f. This is equal to. Okay, now it's actually quite similar to the previous, the start of that proof from a few hours ago. So g. How did that go? So g minus 1 f of x. Actually, make it 1 minus. We'll move it to the other side because g is less than 1. So 1 minus g f of x. So moving it. So we're moving this stuff to this side.
Okay.
Is greater than. So where it gets interesting. So 1 minus fy over yx minus fmy minus d plus gy. This confirmation of that is. But I guess this stuff doesn't really matter. So it's actually a bit different because now g is less than 1, because in the previous thing g was greater than 1.
Minus d, minus g. Yes.
So now this is true for all x. Now we have to see. Now we can see. This has to be less than or equal to 1.
Yeah. Well,
It can. I guess it can take. Oh no, it can't be.
Technically, it couldn't. Like,
Okay, we actually prove it can't. I think it also can't be equal to 1, and I'll show you the reason. So suppose I'll do a separate thing on the side. Suppose there exists an e greater than 0 such that f of x is greater than x minus e. And the reason it fails is because the left-hand side doesn't go to negative infinity. Because f of x plus y minus f of x is greater than f of x minus e. So make x large.
Wait, no, you can't. Wait, you can't do that. Wait, I'm gonna randomly.
Wait, actually, wait. I think I stopped it. Wait, let's restart.
Yeah. I was recording this. Okay. Yeah, it's greater than f of.
Actually, I think we'll just leave it. Actually, we'll just leave it on the inside. We'll just leave this.
You get like that. Right, yeah. It's not that.
Okay, so now, but the right-hand side. So as x goes to infinity. So as x goes to infinity, the left-hand side. The left-hand side is always greater than 0. If we make y, I mean actually left-hand side does not go to negative infinity yet. Does not go to negative infinity, but right-hand side will go to negative infinity if you make y. Y becomes bad.
Ah. If we make the. Oh wait. What about the f?
So since f of k, since f of k is less than k, we make y equals k.
Oh, and then we just choose a
And x goes to infinity, then right hand side goes to negative infinity. So we can make y equals k here as well. So that's the reason why. Yeah. So that means we must avoid.
If I reach avoid the situation.
So that's nothing. Oh, how?
So what it means is that
The king.
G can't. That means G has to be less than 1. Yeah. So yeah, I already have it. So G.
You got a good one.
So G. This doesn't work if G is 1, which means that this has to be less than 1.
Wait, why? 1 minus 3 is obviously.
Oh,
Why this whole thing has to be less than 1?
Why the whole thing?
Because this can be this is a new value of G.
Why?
So this works for a new G.
Why can't it be more than
Because wait.
it's more than 1 then.
Because then if it's more than 1, then this is already satisfied.
Wait.
So if it,
Wait, yeah.
if it works for a larger G, it works. If it works for a larger G, it will work for a smaller G.
Okay. So we proved it can't be larger or equal than 1.
Yeah.
So that's less than 1.
Yeah.
Let's go.
Wait, why can't it be negative?
It can't be negative because are you talking about like 1 minus? No, because both top and the bottom.
Why?
Oh wait, I guess this could it can be negative, but it doesn't really matter. I guess.
I think only cares about this less than 1. But then wait, what? Can you explain why?
Guys doing nothing. Why is less than 1?
Okay. So if this was greater than 1, then f of x is greater than some linear thing that is above 1, that constant's above 1. But if that's true, if this is true, then this will also be true. But this we already know this can't be true.
Wait, if that's true, does that mean we can find an E such that it works for every X?
If what's true?
Oh wait, no, that's obvious. Yeah, okay. Yeah.
Actually, another way of explaining is
No, that's true.
if it's more than 1, then you can use the same contradiction with the going to. This goes to infinity. This goes to negative infinity. Yeah. So now, so 1 minus f of y over y is less than 1 minus g, which means that f of y over y is greater than. So this is actually, if you look carefully, this is actually a stronger statement than this. Because now D is kind of gone. So it's an unusual proof, but it says if a weaker thing is true, then a stronger thing is true.
Wow. That's a very nice way to phrase it. If a weaker thing, stronger thing is true. Okay. Now what?
Okay. So now that means that f of 1. Let's try a random like. That means f of 1 has to be greater than g. No wait. What am I trying to say? Wait. Actually, no. Ignore that. Wait. So that means f of k. So it's greater than gk. So k is the value where f of k is less than. So that means that f of k over k, g is less than f of k over k. So this is important. The reason is you can't make g arbitrarily close to 1. So you can't make. So if f of k over k was 0.9, then g can't be greater than 0.9. So that's. So that's. I guess it looks not that interesting, but I guess it's important. So k, yeah. So just recall k was this value. So now, let's say, suppose we have a value called L, where suppose there exists L. So now I make it 0 less than L. I make it less than equal to 1. Such that where f such that there exists the infinite sequence
That makes you.
So it means there exists an infinite sequence such that f of zn over zn is at most L.
What the hell? Wait a second.
So what it means is that if you find an L that works, then G has to be at most that value of L.
Okay, I have seen. I think I have.
So because we know if we have a working G, we already know this is. We already know that G will be at most that.
Yeah.
And G will be yeah. So that means that if we find the L where this works, then G will be at most that value of L.
Actually, is that strictly?
I'm trying to think. So this is at most L. This is.
Isn't that strictly great?
So which inequality is strict?
The left one, the left one.
You.
It's really.
Oh yeah, wait. Oh yeah, you might be right. Let's double check this line. Yeah, I think that's right. So G. Okay. So the first question. So what we can see is that we have the interval between 0 and 1. And now let's say we have a. So let's say all the values from G. Let's say what are the possible G values.
Yes.
So G can't reach 1.
Yeah.
So you can think of, let's say, the supremum of the G's.
The sub G.
So the supremum of G's. Okay, so actually, better way of explaining it away. So I think you can call this a part connected set. So this is kind of topology. So it's saying, so for example,
Part connect.
A B. If G equals A and G equals B works,
Yes.
then everything in between works.
Yeah.
Or if G, actually, better way is if G equals B works, then everything less than B works.
Oh.
Which means the possible G values is either closed interval or an open interval. It's either of the form. It can either look like this. Say max. Say G max. It's either this or this. And so G max is less than f of k over k.
Yes. That's true.
Okay, let's look at the next part. So the next important step. So we already know this is true.
Yes.
So, but we know f of x over x. If we apply the xn's, if we make this z, if we apply the zn's for x's, so if we make this f of zn,
Yeah, I killed him.
What are these ZNs again? Is it just that they exist? Like they exist?
so we're saying consider an else. So we're not. So we're saying suppose there exists an else such that. Suppose there is some else such that f of zn, there exists an infinite sequence where f of
Is that true?
So I guess it's not really a true or false. It's just saying suppose we can find an L.
Can we find it?
Yeah. So I guess it's kind of in the context of the proof. I think later we'll show there is. So for example, I think everything after the maximum G is going to be an L value.
Oh.
Oh, now I do.
Because
What is going on here?
because L exceeds all the G's. Wait. See. Let's try to explain a bit better. So f of zn is greater than this. Okay, I'll just make this value an. Let's make this an h. So that means f of zn over zn
That's how it be sometimes.
is greater than 1 minus f of y over y over 1 minus g minus h over zn.
Yeah.
This is less than L.
Yes.
So L is greater than this.
Yeah.
And but Zn goes to infinity.
Okay.
So what that means is L minus this. So L minus this is greater than this. So it means this is at least 0.
Yeah, that's
So it can't be, I guess it can't be equal to 0, but it has to be at least 0.
Yeah. No, it's actually. I think L has to be.
No.
Yeah, it's greater than equal to 1 minus.
Okay, here we go.
So now from rearranging comes
19.
Oh wait, isn't that like greater than 1 minus G? The right side. Oh wait,
I guess
that's greater than 1 minus L.
Hang on.
Wait, this one gone.
Oh yeah, wait. I was trying to recall my. What was the next step again?
Ah.
I was trying to recall what was the next step. So f of y over y is at least
Okay, now you can just win.
1 minus GL.
You just won. Yeah.
Oh yeah, I think you can make the y's equal to z's.
Wow. I mean, yeah, I think the Y you can do whatever you want to. Yes. No.
So if y equals zn, and this is at least at most L.
Oh, yes. What the heck?
So now 2 minus G L
L.
is at least 1. So L is at least 1 over 2 minus G.
Yes.
Okay, so L is at least 1 over 2 minus G.
Yes.
And now the question is 1 over 2 minus G greater than G?
Yes. Yeah, it is. No, it's not. It's not. 2 minus 1 squared is greater than 6. Oh, wait, what? Oh. Oh.
Yeah.
Yes.
Yeah.
Yes, it is.
So now L is at least 1 over 2 minus G, which is greater than G.
Wow.
What the
Wait,
frick?
is that even possible? That wasn't possible.
Okay, you win.
Isn't that not possible if we choose L as a supreme?
Oh no, we'll get to that later.
Well, why did I thought we knew L was greater than G?
Alright, but now L is greater than this thing.
Yeah, so we have a better balance.
Yeah.
Okay.
Okay, so now let's try to explain this as best as possible. So now in first case, okay, let's look at this case. So what's wrong with this case?
Possible G's is a closed form of that.
Okay, so firstly, let's say if we first prove if L is greater than G max. Does it work? If you make an L, if you choose any L that's greater than G max, is that a suitable L value? And the answer is yes, because if something was greater than G max, it means that you can't put it into here. So if something doesn't work for G, if G fails, okay, actually we do contrapositive. If G fails, I think we're close to the end. Right? There's some technical stuff So if G fails, that means there exists. So you can't have. Wait.
Is it comprehensible?
No. it's kind of convoluted in wrong one. We'll see.
Okay, if G fails, that means
I don't
that.
see the motivation for any of this, to be honest.
Oh no.
I haven't had any anchoring riddle questions. Let this man roam free.
So f of x. If G. If G is between 0 and 1, then. So you have to prove that if G fails, then it can. If G fails, then we get an L value.
Okay.
And the proof. Okay. So proof means if G fails, there does not exist a D.
My guy just has all the letters.
H to Z.
Entire alphabet.
He's an alphabet. He's an alphabet. He's an
So-
alphabet collector.
There does not exist a D such that f of x over x is greater than G minus C over x. And let's say we make it equal. We make let G equal to the L value. If G is equal to the L value, it means this is going to fail for all D. So we make, I think, it's a similar trick to before. So we make D go to infinity. We make an infinite sequence of D's that go to infinity, and then we get an infinite sequences of X's such that f of x over x is
This guy's
less than
just
G.
dying. This guy's just.
So for each D, so make a for each D. So for each D, we can find an X such that this inequality doesn't work. But X has to go towards infinity, because when D is large, again, it's similar thing before. When D is large, we need X to be large. So then we get an infinite sequence of X's that works. We get an infinite sequence of X's that works, and this satisfies the L condition.
Wait, in this case, it's like lower bound. So even if T is large, not just wait. Oh wait, it's such that this fails.
Yeah. So
Oh yeah.
so you're saying if the G the G we test fails, then it's a suitable value for L. So what it means is, so we have two cases. So the first case is we have an open interval or a closed interval. So that means that everything beyond this can be an L value. So can you see the problem? What's the problem with a closed interval? This maybe you have to go back to. Look at this. So, suppose there was a largest G. So let's say this was the largest G.
Yeah.
But now we have something that is greater.
In between it.
There is something in between G and L. So
It's technically between the value G and 1 on 2 minus G.
so that means, because you can't have all real numbers greater than L working, which means you must have an open interval. So there exists a smallest L that works. So there exists a smallest L. But now you can prove that this sequence, and remember, L has to be less than 1.
Yes.
Wait, I just remember again. Wait, is L less than? Oh yeah, because remember, so G max is less than f of k over k, which means that L is less than 1.
Yes.
Or you can say L is less than equal to f of k over k. Which means that G max, the G's don't approach 1, so this value can't be equal to 1. So the supremum of G can't be 1. And now we prove that, but now the contradiction is we prove the infinite sequence Gn plus 1 equals 1 over 2 minus Gn approaches 1.
Oh.
So the limit. So this is already an increasing sequence. So we can just prove. We can just do the trick again. So limit of. Suppose. So this must. I guess this must have a limit. So limit of gn plus 1 minus gn.
Oh my god. Oh my god. Oh my god.
So gn squared minus 2gn plus 1 over.
Yeah, well, that's not doing well. Wait,
Okay.
is it negative? Wait, that's right. Is that right?
And so this is
Oh,
meant
it
to be.
is.
This is
Negative.
meant to be 0. And the only way this can be 0 is if gn goes to 1.
Oh.
So gn must approach 1, which means that the supremum of the g's is at least 1, so that's the contradiction.
That's crazy. Wait, that's actually crazy. So that means there's no L, right?
Anthony, do you have like bone block?
Yeah, so it means that.
That means
What? Bone block.
So if the supremum of g's is 1, the problem is that
I don't know.
all g's. I guess all g's are
Bone block.
all g's are less than f of k over k. But f of k over k is a fixed number that's less than 1, so you can't bridge a gap. So you can fix a number that's less than 1, and g's can't pass that gap.
You not know where the phone block is.
So it's a real analysis proof.
Yeah, that's done. That's it.
Real
done?
analysis.
Oh, it's a contradiction. That's a contradiction. Bruh, how did... It's like a magician pulled out 5 tricks that you just never see in your life, and you actually, like, you don't know what's going on now. Like, you've seen it with your eyes, where you're just like, what?
I feel like Yasiru and I are just more interested in limits.
I think it's just a uni.
Limits are so hard. Like they're like so niche to use because they're like they sometimes they don't work because you don't define them properly. And like
Let's see.
The notoriety of the limits.
yeah,
I think it does require some care. So I think the stuff like defining L. So I think there's stuff like. So I guess even though some stuff seems obvious, but still needs some explanation, such as think about if a G, for example, if a G value fails, then it must be an L value. So I guess it feels obvious, but it still
Why
needs
does he, dude? He's using every letter in it. I don't understand the whole deal.
So now
I
I might reveal a secret which I withheld, which was that I think the original proof last week was a fake so.
yeah, it was. Yeah.
That's why I didn't really want to mention it to discourage you, but I saved it.
You saved it.
So that's the reason I did this. So,
Yes.
Improved proof.
actually, if I didn't come up with a proof, I could have just not told.
No one would have known. No, I'm not even joking. No one would have like properly.
Because I think the problem was the last week's proof I actually put a 1 minus c somewhere where it should have been the c. Because I mixed up the 1 minus c's and c's because I defined c as the g stuff. I mean the f of y stuff.
Yes.
So the withheld secret